Install a standard general-purpose gasket into an aggressive industrial pipeline, and this is the result: high-pressure steam violently bursting through a bolted joint. It is a common mistake to check the chemical compatibility chart and stop there. A material might be completely inert to the acid flowing through it, but if it cannot handle the physical thermal expansion of the pipe, it will fail. This diagram maps out the 3 root causes of gasket failure. First, chemical degradation, using the wrong material for the media. Second, mechanical blowout or creep, which usually comes from choosing the wrong thickness or style. And third, installation error, like uneven bolt torque. As you trace these branches down to their outcomes, you see that taking shortcuts during the selection process to save a few minutes of upfront research directly leads to toxic leaks and expensive plant shutdowns. Selecting the correct seal is a mechanical engineering calculation. You have to balance a material's ability to conform chemically with its ability to remain physically stable under intense stress. This is the STAMP framework. It stands for size, temperature, application, media, and pressure. It is the mandatory checklist you need to run through before evaluating any flange connection. Starting with the M, the media dictates the chemical resistance required. You need to know exactly what is flowing through the system, whether that is water, strong acids, or hydrocarbons, to ensure the gasket will not dissolve on contact. Moving to temperature and pressure, these variables test the physical limits of the material. They determine if the gasket will melt, become brittle, or blow out under the system's operational loads. Finally, application and size cover the mechanical realities of your equipment. This includes the specific type of flange face you are working with and the physical dimensions required to properly seat the seal. Applying this framework requires rigorous initial engineering, but running these 5 variables is the only proven method to ensure long-term operational uptime and zero leakage. Let's look at the actual materials, starting with EPDM. EPDM is excellent for water and steam systems operating up to 150 degrees Celsius. But if you put it in an oil pipeline, it will break down almost instantly upon exposure to hydrocarbons. For oils and fuels, NBR, or nitrile, is your cost-effective workhorse. However, it is strictly limited to lower temperatures, typically around 121 degrees Celsius, and it cannot handle strong acids. When dealing with harsh environments, Viton is the premium upgrade. It provides outstanding resistance to solvents and hydrocarbons, and it can survive extreme heat up to 200 degrees Celsius. If you are processing aggressive acids, virgin PTFE is the universal choice for maximum chemical inertness. It resists nearly every strong chemical in a plant. But this diagram illustrates PTFE's critical physical vulnerability: cold flow, also known as creep relaxation. Watch how the material slowly flattens and spreads outward under compression. As it thins out, the bolts lose tension, compromising the seal. Now compare that to a flexible graphite gasket. As intense heat and pressure are introduced, the graphite holds its shape flawlessly. It can handle extreme steam temperatures up to 550 degrees Celsius with zero creep. But graphite has a major limitation. If exposed to a strong oxidizing fluid, like concentrated sulfuric acid, the material rapidly oxidizes and falls apart. There is no single perfect gasket. Achieving chemical inertness almost always requires a trade-off against mechanical stability, cost, or thermal limits. When maintenance teams face a damaged or pitted flange, a common reaction is to install a thicker, non-metallic soft gasket to fill the gaps. But in reality, this is a dangerous misconception. This is a pressure times temperature, or P times T, line graph. It shows 2 intersecting curves for the same material at different thicknesses. Notice how the thicker gasket has a dramatically lower safe operating zone compared to the thinner one. Because a thicker, soft gasket has higher compressibility, it is far more susceptible to being pushed out of place. As system pressure spikes, it crosses out of the safe operating zone, triggering a high-pressure blowout. To avoid this, engineers use structural alternatives, like metallic spiral-wound gaskets. With a metallic gasket, the maximum pressure limit is dictated by the strength of the flange itself, rather than the thickness of the seal. The trade-off is that metallic gaskets demand a much higher compressive load to seal properly. If you tighten one against a fragile plastic or glass-lined flange, it will crack and destroy the equipment. If your system dictates a non-metallic gasket, remember that thicker does not mean stronger. Specifying the thinnest possible material profile that can still conform to the flange is how you prevent catastrophic pressure failures. Once you decide a spiral-wound gasket is necessary for your high-pressure system, you have to configure its exact architecture to match your specific flange face. Here is a top-down schematic of a spiral-wound gasket, showing its 3 distinct layers. The inner ring protects the soft V-shaped filler windings from the harsh process media, and it prevents the gasket from buckling inward under vacuum. If the system uses a raised face flange, you need a gasket equipped with both inner and outer rings. The outer ring perfectly centers the gasket against the bolts, keeping it locked in place to prevent a blowout. Never attempt to seal mismatched flanges. If you bolt a flat face to a raised face, the gasket experiences an uneven pinch. That creates a gap on the outer edge, guaranteeing a leak. These components are physically fragile before installation. If a technician carries a large spiral-wound gasket by the outer ring alone, the inner windings can sag and dislodge under their own weight. You can specify the highest-rated metallic gasket on the market, but if its architecture is mismatched to the flange, or if it's damaged by improper handling, it will fail. Even the most rigorous material engineering and stamp analysis can be instantly undone by human error on the floor during final installation. This diagram compares flange tightening. A circular sequence unevenly crushes the gasket. A numbered star pattern ensures a flat seal. Executing multi-stage torque passes, 30, 60, and full torque, generates the uniform load needed. Finally, re-torque bolts after the first heat cycle to counter thermal relaxation. Skipping the torque sequence or the retorquing phase might save a few minutes of wrench time today, but it is the leading cause of immediate seal failure and blowout tomorrow. To summarize the baseline chemical rules, use EPDM strictly for water and steam. Always specify NBR for oils and hydrocarbons, and upgrade to Viton when dealing with extremely harsh environments. Never select a gasket based on its pressure rating alone. You must calculate the holistic PXT value to account for how thermal stress weakens the material. Before ordering rigid spiral-wound gaskets, physically verify your flange face compatibility and confirm the flanges can handle the required bolt loads. For soft gaskets, thinner materials provide better pressure stability. Before final assembly, verify your STAMP match, confirm flange compatibility, and always apply a star pattern torque. Navigating these engineering requirements with discipline is the only way to guarantee long-term operational uptime, protecting both your personnel and your facility's bottom line.